inquiry one. Quakes, plates, and waves. Oh my. Okay. My idea for the inquiry was I'm in a geology class. I'm in a geology 300 class. I've never had prereqs for geology, so when my teacher starts talking about different things we're learning in class, I didn't know half the stuff she was talking about, so I had to go back and teach myself certain, I guess, terms. And some of the terms she was using deal with different plates and ridges and things. And my inquiry is based on P waves and S waves, primary waves and secondary waves. Now, the reason we know these waves exist is because of the lithosphere, which is the Earth's crust and the Earth's mantle. And we know these plates and boundaries exist because of earthquakes and volcanoes. Now, let's see. Earthquakes, okay. This is a picture of, I found it online. In 2011, there was an earthquake near Alaska, and this dark blue line just shows how the earthquake, where it started underneath the ocean, and different, let's see, sorry, backtrack real quick. There are different types of boundaries. There are divergent, which cause, sorry, I'm still learning some of this information, so don't mind me. Okay. Divergent are in the ocean, which like do ridges in the ocean floor, like the not canals, but like caverns, kind of valleys in the ocean. And those boundaries are going to move opposite each other. They're going to go different directions, which would cause the floor to separate, creating a valley. The next type of plates are going to be convergent, which there's 3 different types of convergent. I'm not going to go into those today because it's not really relevant to what I'm going to be doing my inquiry on. The third type of boundary is a transform boundary, which is where rocks will slide next to each other, causing earthquakes. And that's what my inquiry is on today. This is an example of what I was just saying about transform boundaries. They move next to each other, which creates the rocks to slide and kind of vibrate, creating an earthquake. This is, I guess, a seismograph example of a P wave and an S wave and what they would look like on a seismograph that I guess they would look at when an earthquake hits. Now, P waves, or primary waves, are the type of waves that can go through the Earth's crust and the mantle, and you can, like, if there was an earthquake in California, you would feel it, or you could feel the remnants of it in, say, Virginia. Secondary waves are the slower of the 2 waves, and they can go through the inner core, but cannot travel like across the United States like a primary wave could. Now, to demonstrate the different types of waves, my roommate and I used slinkies to simulate what a P wave would look like if we could see them, and what an S wave would look like if we could see them. Now, on our first trial, when we first used the slinkies, we didn't really think closely enough about it, so when we did the experiment, we, as you'll see, we really didn't realize how hard of a deal it would be. Well, I'll explain since my video will not work. I had her stand 6 feet from me, 2 meters from me, and I was holding one of the slinkies and she was holding the other end. Now, she was supposed to keep her end stable and still. So when I took my end and would shake it up and down, or excuse me, not shake it down, push it out and towards me to simulate a primary wave, you should have been able to see the way the slinky moves and everything. What we didn't account for was me and her standing so far apart and the slinky being so heavy that it kept moving. And it was difficult for us to time exactly when it got to her and then back to me. Because, again, the slinky was heavy and it wouldn't stand still. So that was our trial 1, and we did that a couple times before me and her turned around and realized we have linoleum in our bedroom. We can do it on the floor and be able to see the actual wave much better. All right, this is our primary wave simulation.
Do you have your jump drive with you?
No, I emailed it to myself. Well, as you can see, she is at one end and I'm sitting down over here. And this would have been a primary wave. And I'm actually, thank the heavens, found a picture of what it would look like if I were to push or pull towards me and then push to her. The wave would start like this and then, excuse me, put this way. It would start out that way, go slowly, and then hit here and would bounce back. Compression, dilation, and then compression again. Now for my secondary wave simulation. We're going to see if it would play if I just click on it here.
If the movies are on your jump drive, it's not going to. That's probably the issue. They're not embedded once they're on the jump drive.
Okay. Well, I apologize for my videos not working, but on the S-Waves, again, we're on the floor sitting down, and I had my end where I would be moving it, and she held her end steady. And for the S-Waves, to simulate them, you would take my end of the slinky and shake it side to side, and the motion of the slinky would look something like this. It would start out me shaking one way, it would go the opposite way all the way to her, and then it would, once it hit her, it would do the same back towards me. We did this for each wave, we did this 10 times to get an accurate amount of data. And these are the times. When doing my research for the single IRE, I found that primary waves are a lot faster, can travel a lot faster, and that secondary waves tend to be slower when they travel through the earth and the core and everything. So in doing my inquiry, we did find that the S waves were a lot slower, and I wasn't sure what kind of graph to do. I tried a couple different ones, and my Excel was yelling at me. So I just went with a bar graph because it would show how faster the primary waves were compared to the secondary waves. Primary waves are going to be the blue, and the red are the secondary waves. Just to reiterate, primary waves are the push-pull waves, and they affect the rocks beneath the surface by, let's see, primary waves affect the rocks beneath the surface by vibrating them, which is going to make the buildings move back and forth during an earthquake. And secondary waves also vibrate rocks beneath the surface, but they are the ones that make the buildings and everything shake and like vibrate themselves. Both waves are high frequency waves and cause buildings to move and shake during earthquakes. Question?
What was your research question?
I just wanted to see how quickly they were compared to what I had found online. So I wanted to learn more about the two different waves and how they affected, I guess, the earth during earthquakes.
Okay, so state in a couple of sentences what your conclusion is.
My conclusion for inquiry 1 is primary waves are faster than secondary waves, and even though they're both high frequency waves, primary are going to be the ones that you feel first and feel the most.
What was the picture on your very first slide with all the red dots over it? Yeah, what is that?
Oh, what that's showing is, we're learning in geology how there's active continentals and there's passive. The red is going to show an active area. So on the, on the coastline of South America, all these red dots show active plate boundaries, which means that they can cause either earthquakes, volcano eruptions, different ridges and things forming under the ocean and everything. Just means that they're active compared to like, there's not very many in Australia that are active.
And are all the red dots volcanoes?
No, it just shows that those areas are going to be active.
Okay.
Will you go to your data, please? Okay. What else could you do to describe the data besides a bar graph? What other way can you express your findings?
I attempted to do what I thought would be like a line graph, but I couldn't determine how to, because the distance was the same in each trial that I did. So I wasn't sure, and I tried different things, and none of it seemed to work the way that I had envisioned, I guess.
But you were trying to find out something about the speed of the waves, correct?
Mm-hmm.
Thinking about that, what's something you could mathematically do to determine something about the overall P waves and the overall S waves? Anybody want to help?
Let me ask you, if you're a teacher and you have a gut feeling that the girls in your class have a higher IQ than the boys in your class, how could you support that? How could you see that that's true?
I guess through coursework and like exams and such.
You could go to their files and look at their IQ scores. Now, what might you do mathematically to be able to make the statement of, I believe my girls are smarter than my boys?
I'm not sure.
What about you go to class and you take 4 tests, and Joe Dan goes to class and takes 4 tests, and you know your 4 scores, you know his 4 scores, and you say, Joe Dan, I think you're doing better than I am. Mathematically, what might be one way to measure that? What do we normally do with those 4 grades?
Like
You
average.
You just said the key word right there.
Average. Gotcha.
So find the average of the average time for the P waves and average time for the S wave, and you say son of a gun, by golly, it is shorter.
Any other questions, comments?